In this video, we're going to do a review of balancing chemical equations from scratch, where we're also going to discuss how we actually get the formulas for all of the different chemical compounds you see in this example. And to distinguish this from my other videos, this is balancing example number 1. So this says sodium carbonate solid and a nitric acid solution react to produce sodium nitrate, carbon dioxide gas, and liquid water. So this first compound that's listed, sodium carbonate solid. So sodium, if we take a look at our periodic table, sodium is right here, Na. So the symbol for sodium is Na, and because it's in that first column of the periodic table, and it's on the left side with the metals, it's going to be positively charged, and it's going to specifically be a +1 charge. The carbonate, that is a polyatomic ion, and the formula and charge of it you do need to memorize. It's a CO3 2-. So to get the formula for sodium carbonate, you want to think to yourselves, in order to form a neutral compound, how many sodium ions are going to be needed to balance with one carbonate? Since sodium is 1+ and carbonate is 2-, the formula would end up being Na2CO3. And since they did say it's a solid, we will just label it as a solid for the physical state. All right, next up, a nitric acid solution. So nitric acid, that comes from the polyatomic ion nitrate. So the nitrate turns into nitric when you take the polyatomic ion and make it an acid. And then since it is an acid, we're going to call it HNO3 instead of just NO3. The H being hydrogen, which is +1, and the NO3 is 1-. So just one hydrogen, one nitrate makes that a neutral compound. And then it does say solution, which means we can label it aqueous. So that means it's dissolved in water. So then react. So I'll draw my reaction arrow. And then we're producing sodium nitrate. So again, sodium is that Na with a positive charge. Nitrate is the polyatomic ion NO3. And since they both have a charge of 1+ and 1-, we only need one of each to make a neutral compound. So sodium nitrate would be NaNO3. And then for the state of matter for NaNO3, you want to think about your solubility rules. So the simplest solubility rules that we usually ask students to memorize is that all alkali metals, so that first column, if you see those, it'll make it soluble. If you've got nitrate, it'll make it soluble. So I'll say group 1 metals. Nitrates, if you see that, it'll make it soluble. And another rule is if you have ammonium compounds, that rule is not going to be used in this example, but those are the 3 simplest rules that we usually ask students to memorize because those rules do not have exceptions, but there are more rules than that. But anyway, point being, according to those rules, sodium nitrate would be soluble in water, which means we would label it aqueous. Next up, carbon dioxide. So that nomenclature we see, that's for a covalent compound where you have nonmetals bonded to nonmetals. So carbon dioxide means CO2, and I did say it's a gas. And then, of course, water, H2O, and I'll label it liquid. Okay, next up for balancing. Now, one strategy for balancing is you can draw a column, and even when you do this column, there's still multiple approaches. So one thing that we can do is we're basically going to write out all of the elements that we see in this equation, and then we're going to just kind of count up how many do we have on the left and the right side, and then through trial and error, we're going to use this column to kind of keep track of our work until we end up with a balanced equation. And the other strategy, which I'll show you after this one, is we can keep certain groupings, like the nitrate. We can keep it as one grouping since it's not changing, but I'll demonstrate that after we finish with this first strategy. So on the left side, I see we have 2 sodiums, so I'll put a 2 right there, and there's 1 carbon, so I'll put a 1. I see a total of 6 oxygens, so I'll put a 6 right here. And then there's 1 hydrogen and 1 nitrogen. So that's my current head count on the left side. On the right side, I have 1 sodium, one nitrogen, carbon, I have one right there. Oxygen, I have 6, and hydrogen, I have 2. Okay, so it's not balanced already, so there is some work to be done. What I usually do is look for kind of what I consider the rarest element. I mean, hydrogen appears a lot, oxygen's pretty common, carbon's pretty common, but like sodium, we don't see sodium too often. So my strategy would be like, okay, what can I do to fix the sodium and bring that so it's balanced? Well, if I put a 2 right here, that would make my sodiums balanced. So then what you do is after you insert a coefficient in front of a chemical compound in the reaction, you need to check your counts for all the elements that were affected. So my sodium on the right side becomes 2, of course. The nitrogen goes from 1 to 2. And the oxygens, I just added 3 more essentially. So I've got 6 from here, 7, 8, and 9. So my oxygen should now be 9. Okay, so now I see that, let me change colors again. I'll change to this. Anyway, so my nitrogens are now out of balance and my oxygens are out of balance. And my hydrogens as well. So it's like, oh gosh, I got a big problem. What am I going to do about that? But if you look closely, if we put a 2 right here and then check it, so my hydrogens would now become 2, my nitrogens become 2, and my oxygens, I've got 3 here and 6 here. The oxygens become 9, so we're good. Now it's balanced. So that's doing it by like every single individual element, and this is one of the first ways that I learned how to balance chemical equations. But I'd like to show you another way. This is particularly helpful if you've got polyatomic ions involved, and the polyatomic ions are not breaking up. So we're kind of keeping track of them as units instead of as individual elements. So what do I mean by that? I'll first write the elements that are not in my nitrate, because basically we're going to focus on the nitrate. So I've got sodiums, carbons, and then I have hydrogens. And then I'm also going to do oxygens that are not in the in the nitrate. And then I'm going to treat the nitrate as like its own separate thing. This is kind of a little bit of a shortcut. It can make your counting easier, especially given we've got like oxygen in 3 places on the product side, so that can make it a little bit messy. Anyway, so now inserting, or actually doing the head count. So like sodium is on the left side, I have 2. Carbon, I have 1. Hydrogen, I have 1. Oxygens that are not in my nitrates, I have 3 from that carbonate. And then the nitrate, I have 1 nitrate. Okay, on the right side, I have 1 sodium. I have 1 nitrate, that's from that. And then I've got the 1 carbon in my CO2. I've got the 2 hydrogens. And then oxygens that are not in nitrate, I have 3, 2 from carbon dioxide and 1 from water. So doing it this way, hopefully you can see that it's really just like the sodium. Let me see. It's the sodium is out of balance and the hydrogen's out of balance. So let's see, we could do kind of the same thing. Let's put a 2 over here to fix the sodium. So that means this becomes a 2, and now my nitrate becomes 2. And now the things that are out of balance, the hydrogen and the nitrate, but then we could put a 2 right here to get the hydrogen and the nitrate in check. Now this other strategy, it wasn't particularly graceful for this reaction, but if you have a double displacement reaction where you're forming a precipitate, it can be especially helpful to just focus on the polyatomic ions as units instead of focusing on all the elements, especially when you've got polyatomic ions where both of them have oxygen, and it can get pretty messy pretty quickly. But anyway, I hope this video was helpful.